Hello, welcome to this video about GPS systems. I will give you briefly an overview about the main and the most important information about GPS. First of all, when we speak about mapping GIS, we have to distinguish three main components that will lead us to the data collection on the field. We have a GPS receiver to get the data from the satellite, the information, with tablet PC or a handheld, and then there is a processing and GIS software, and the GVSync is one of them. Then what is mapping GIS? It's an activity to measure, process, and manage field data of different kind of data, environmental, urban, road, and so on. We have to collect data, geometries as well as attributes. We can have a real-time navigation and survey, as well as real-time georeferencing field data, taking photo, notes. I will show you some software to do this. How GPS works? The Global Positioning System, that stands for GPS, is a constellation of satellites used to calculate our position on the ground. And how do we use these satellites to calculate our position? Let's say that let's think to imagine to use transmitter on the ground. We can calculate the distance between the receiver and the emitters through the equation time difference times speed of light equal to distance. So in this case, we can have in any place around this circle. But if I have 3 circles, I can have only on this place. On the contrary, if I had 2, I could be here or here, let's say. And then the similar, if we think about the satellite, so if we are on the ground and we receive information from the satellite, the receiver is somewhere on a sphere with this radius, the distance between the satellite and the receiver, or let's say the surveyor. And I have to calculate the exact position x, y, and z. Then if I have 2 satellites, I could be any places on the intersection between the 2 spheres, but I need to define exactly the point, not anywhere in an intersection. Thus, I need 3 satellites. In this case, the 3 satellites identify exactly a point in which the 3 spheres intersect each other. So 3 distances help me to solve latitude, longitude, and height. But I need as well to define the time, defining the time information. So basically, when I'm in the field, I need to look, let's say, my receiver has to see at least 4 satellites in order to define latitude, longitude, height, and the time. So basically, when you are in the field and you look for satellite on the sky, just wait for having at least 4 satellites, and always usually the GPS starts to give you the position only when they see the signal of 4 different satellites in the sky. So we have 3 segments in GPS. The space segment is, to say, the satellites. The control segment is, let's say, the receiver from the ground, and then we have as well the user segment, let's say the private person, the surveyor, who get the information directly from the satellite, and the control segments can spread this information nearby. There are some system errors that you have to consider. Let's say the satellite errors are uncertainty of the orbit, as well of maybe the clock drift. There is a clock inside the satellite, and there is receiver error as well. I can have a clock drift inside the receiver, and there is as well some signal error due to the ionosphere and troposphere that the signal has to pass through. And how I can get more accuracy? I can get it by using differential GPS that allow to get more accuracy. And so I can have two GPS receiver, one master and one rover. Let's say the master is called as well reference station, and the simultaneous tracking of at least, as I told you before, 4 or more satellites for both GPS. So then I have the absolute coordinates of the receiver that it's not moved, let's say it's in the same position, and a processing differential software supporting me to calculate exact the position as well of the rover. Then we get from this process the elimination of clock errors and the minimization of atmospheric errors, both of them. So as a final result, I get an exact definition of the baseline of the distance, and by consequence, I will be able to define exactly with extreme precision the position of B. I have some operating problems when I work in the field, such as multipath error or interferences. Let's say if I have a wall, my receiver can get the signal through the wall, so let's say it's not an exact signal. Or as well, I can have some electromagnetic interference, some radio signals, power lines, and so more. So these problems can give you some bad measurement, as well as obstacles. If I take a point under trees, for sure the signal cannot reach the antenna of GPS. Thus, let's say the solution is multipath interference. The antennas of GPS receivers perform automatic correction for screening the messy signals. So they will get only the back signal acquisition, and they mitigate the noise through some dedicated filter I have in the machine, in the equipment. And obstacles, to solve this problem, you can performing out of center. I will show you how to measure field location and positioning and calculate the position through some formulas, or planning the survey with a software. How can I evaluate the measurement? There are some parameters. It's called DOP, dilution of precision, that describes the decrease of precision to process the coordinates of a point based on the distribution of satellite in space, and it's a quality indicator of geometry satellites tracked by GPS receiver. I have GDOP, geometrical, PDOP, HDOP, and VDOP. So basically, GDOP is include latitude, longitude, age, and time. You see, if I have the satellite all close each other, I have a poor GDOP. On the contrary, in this case, it's a good GDOP because you see that I have the satellite spread all over the skyline. And so let's say that basically the GDOP ranges from 1 to infinity, but usually it cannot acceptable values higher than 8. So GDOP, if a GDOP is lower than 8, it means I have a good GDOP and then my measure is accurate. Then I can set up also, when I make some field survey, a cutoff angle, and it's the minimum elevation angle below which no more GPS satellites are tracked by the sensor. So obscure the satellite tracking low because most affected by noise of the signal due to the troposphere. And so I can set up my cutoff according to the application. Let's say if I want some precision measurement and monitoring, I can set up a cutoff between 15 and 20, for example, for topographic application from 10 to 15. And for JS general application, I can set up a 5. So the low angle decreases accuracy and the high angle increases the DOP. So I can also work in different way. I can work as post-processing. I mean, I can compute position not in real time using data, but I record data on the ground and then I process them in the office through dedicated software. So I have no data on real time. Or as well, I can have real-time data, maybe through radio signal or through the web. I can immediately send the collected data through my office or through my computer directly in real time. So basically, before planning a survey, you have to define which is the precision you want, which is the equipment you need. So basically you can have some differential GPS for, let's say, high quality survey, or a standard GPS cheaper for normal survey with you don't need high precision. But for sure remember that if you increase the cost of products, basically usually you increase as well productivity. So the first thing is you have to consider which is the result you want to achieve, and so which is the best GPS that fits your needs. Then I hope you enjoyed this short video, and keep in touch. Thank you so much.